Hello, I've got a couple of problems I'd like to go over that involve factoring trinomials with a leading coefficient that's not 1. So notice this polynomial here, it's a trinomial because it has 3 terms. It's in descending powers order. Whenever you factor, you want it in descending powers order with, it's an exponent of 2 and then 1 and then a constant. Now, this definitely has a leading coefficient that's not equal to 1. The leading coefficient is -3. What you should always do when you first approach the directions of factor is look for a greatest common factor. And this particular example does have a greatest common factor of -3. So I can divide each of these by -3. Now, what we do when we do that is pull the -3 in front and divide each by -3, and so that would give us a squared. -21 divided by -3 is plus 7a, and then -18 divided by -3 is plus 6. Now, students that have a hard time with that, a good thing to do is write the -3, or whatever your greatest common factor is, below each of the 3 terms and then simplify. So this -3 cancels with that -3, and there's that a squared that we discussed. -3 goes into -21 plus 7 times, and -3 goes into -18 plus 6 times. Of course, there's still an a with that term. So if that helps, definitely do that, and that's for factoring a greatest common factor. Now continue this problem. Notice now the trinomial that's left in the parentheses does have a leading coefficient of 1 now. So we can use the techniques that we used in the section before. We're trying to find numbers that multiply to equal the constant value, which is 6, and also add to equal the middle coefficient, which is 7. And there should only be one pair or no pair of numbers that do this. And so if the trinomial inside factors, there will be one set of numbers that makes this true. If it doesn't factor, you won't be able to find a single set. But numbers that multiply to be 6 and add to be 7, it's going to be 6 and 1. No other way you could possibly do it. So to continue our factoring, the -3 comes down, and we're going to have 2 sets of parentheses. And inside, what goes first is a times a, because a times a gives me a squared. And then what goes next for these binomials is going to be a plus 6 and a plus 1. In other words, we're using these 2 values right here to multiply to be 6. And this is completely factored. Now for the second example, same directions, factor completely. Once again, we have a trinomial that's in descending powers order, as it should be, squared term into the first, and a constant, and the leading coefficient is not 1. This, once again, does have a greatest common factor. 3 divides into both 63, 150, and 75. So I'm going to divide each of these by 3, and don't forget to pull the 3 out front. So 3 goes into 63 21 times, 3 goes into 150 50 times, and 3 divides into 75 25 times. Now, this problem differs from the last problem in that we don't now have a trinomial with a leading coefficient of 1. It's 21 now. So the method we used earlier, what multiplies to be 25 and adds to be 50, will not work for this problem because there's still a leading coefficient that's not 1. And so you'll see something called the AC method, and what that means to do is you multiply A, which is 21, times C, which is 25. So that's the first step. So multiply A times C, so I've got 21 times 25, and that equals 525. So in this case, I'm going to try to find 2 numbers that multiply to be 525, which happens to be A times C, and adds to still be the middle coefficient, which is going to be 50. So what numbers multiply to be 525, excuse me, and add to be 50? Now when the numbers get big like this, it can be challenging to find the values that multiply to be this big number and also add to be 50. You can just start going through the factors. I mean, it could take a while. 1 times 525 certainly doesn't add to be 50. 2 doesn't go into 525. 3 actually does go into 525. See, 525 divided by 3 is 175, but clearly that doesn't add to be 50 either. 4 doesn't go in there. 5 does. 525 divided by 5 is 105, but once again, that doesn't add to be 50. We know they're both positive. That's the only way you add to be a positive number. So I have to get bigger, and then you may just want to guess. What worked actually is 15 times 35. So again, if you multiply that together, that gives you 525, and it does add to be 50. 15 plus 35. Now, so again, this could take a little while. You have to be patient. But what do we do with those two numbers? You don't write n plus 15 times n plus 35 like we did on the last problem. That's not going to work. What you do is you rewrite the middle term using these two values. So I'm going to replace the 50n, and I'm going to use 15n and 35n in that spot. So here we go. 3, don't forget about it in the front. I have 21n squared plus, again, I'm removing the 50n. I'm going to replace that with 15n plus 35n plus 25. Now, that doesn't look like it helped at all. But now we're going to do something called factor by grouping. I'm going to group these two terms together and these two terms together and pull out the greatest common factor for 21n squared plus 15n. So this 3 that's out front still remains. Don't forget about it because it's so easy to do that. The greatest common factor for 21 and 15 is 3. And notice they both have an n. N to the first is the largest that comes out. Now 3n divided into 21n squared is 7n. And 3n divided into 15n is plus 5. I'm going to do the same thing over here by finding the greatest common factor for 35n and 25. And that's going to be 5. And that's going to leave 7n plus 5. Now, to perform factor by grouping, these must match, okay? So if they don't, that means you either factored improperly at the factor by grouping step when you pull out the greatest common factor, or you picked your two numbers incorrectly over here when you did the AC method. Now, we're not finished. The last step for factor by grouping is to write down the one that matches. You're factoring that 7n plus 5 in the front times what's left over, which is going to be 3n plus 5. Now, the good news is you can always check these. To check them, what I would do is multiply those together first, use the full method, then run the 3 through using the distributive property, and make sure you get your original polynomial back. I hope this helps. These just take a great deal of practice, and sometimes working with large numbers like we did over here to the right. Hope you have a great day.